University of Western Macedonia, empowering your future.
Let me inform you that we are going to record the webinar and we'll upload it to the YouTube channel of the University of Western Macedonia and the Electrical and Engineering Department, Electrical and Computer Engineering Department. And let me introduce you Professor Symeon Chatzinotas. Professor Symeon Chatzinotas is a full professor and the head of the research group SICOM in the Interdisciplinary Center of Security, Reliability and Trust of University of Western Macedonia of Luxembourg. Sorry. Actual professor, we want you here, so you see this is an invitation also. Just joking. He is also a adjunct professor on the Department on Electric System in Norway University of Science and Technology, and a collaborative scholar of the Institute of Informatics and Telecommunications in the National Center of Scientific Research at Democritus. Work with Symeon in several things, but today he's going to present a new area for me about the quantum technology and the role that it will be playing in communication. So, Professor, the floor is yours.
Thank you very much, Alexander, for the introduction and for the invitation. I'll just put my slides on the screen, and then we can kick this off. So hopefully you can see them right. Okay, great. And I assume I have about 1 hour, including questions for this?
Yes, you have 1 hour.
Okay, excellent. So there is a lot of material, so I'll just dive right into it. So today's talk is quantum tech for communication systems. Before I start, I'll just give you a brief overview of who we are and what we do. So I run a project, a group called SICOM, which is based in Luxembourg. The research center is called S&T. And we have been operating for about 14 to 15 years now. We have 80 researchers working in various areas. Of course, 6G is somehow the umbrella of bringing everything together, but more specifically, we work on non-terrestrial networks. So this has been something that we target since the beginning, along with massive antenna arrays. But the quantum part has been more recent. So we have been working on that for about 4 years now. But of course, it's a very upcoming area, and we already managed to produce a fair amount of output. So today I will try to give you a bit of a tutorial covering some basic aspects, but also highlighting some of our contributions. So the outline of the presentation goes as follows. So first, some introduction, bringing up the second quantum revolution and where we are today. Then splitting the presentation in two parts. The first part is on quantum codes, focusing on key distribution problems and more visionary quantum Internet aspects. And then looking into quantum optimization for traditional communication problems that we already face in some cases, and they will be even more accentuated in the context of 6D. Then some conclusions and road mapping at the end. Now, second quantum revolution. So this is a very famous quote by Richard Feynman. So we have to somehow admit and even try to incorporate in our research that in reality nature isn't classical, right? So classical is essentially the part of physics which is microscopic, right? So we have some continuous phenomena, and we can have some digital simulation implementation. But if we really want to emulate nature, even going down to a microscopic view, then we unavoidably end up with quantum mechanics. And then we have some strange concepts like the wave-particle duality that can be only fully, let's say, emulated or simulated if we really go into quantum simulation and implementation. So this is essentially a very high-level view of what quantum is trying to achieve. And of course, this is not recent. So the physicists have been working on the principles of quantum mechanics already from the 1920s. And here I have a historical overview of the most important milestones in this area. Maybe I can cover some of them. Most important sample. So you can see the first circle around the EPR. So this is more or less the study that led to the entanglement. Then 76, already people started talking about quantum information theory. 1980, you have quantum computing. 84, you have the cryptographic keys, even before actually Shor's algorithm, which it's one of the most threatening algorithms that came up because it actually challenges the current cryptographic methods that we are using. And of course, moving more into the future, you see that 2017, we start having companies that produce commercially relevant quantum computers, qubit annealers. We have satellite-based entanglement distribution in 2017. And 2019, we have first commercial quantum computers. And of course, even more recently, you might have seen that we even have some quantum computers now that claim to have 1,000 qubits. Just checking if you can hear me fine, because I lost somehow the video.
Yes, we can hear you.
Okay, great.
I don't know why the video. Oh, it came back.
It's back. Okay, good. So then, moving on, these are the pillars of the second quantum revolution. And of course, I'm not going to be covering everything here. Mainly, I'm focusing on the communications part, which is bottom right, and also computing, but for communications, not general quantum computing and what can achieve. There are other parts like the quantum simulation, the quantum sensing, and these are also very relevant areas that are coming up, but we haven't really touched on those yet. Now, just to show you how fast things are moving nowadays, this is the depiction of the quantum computing companies in 2017 or pre-2017. And this is what a partial list of what you have today. So, of course, that gives you the understanding that is a very rapidly developing area. Even though we still have a lot of work to do to make it practically relevant, you can see the volume of brain matter and also funding that goes into these ventures. Now, we can start with the first part. As I said, the first part focuses only on quantum communications infrastructure. And I'll start with a general introduction. So, quantum comms, it's important to understand that they're not meant to replace the classical digital systems that we have. Rather, they will provide a quantum overlay that will have an advantage in certain application areas. But always it needs the classical digital part in order to enable the operation of quantum networks. Now, the near-term vision and where we are today is we have small-scale functional quantum networks in the lab, research prototypes, and we are striving, in some cases this has been achieved already, to have some large-scale quantum key distribution networks, so commercial-grade networks with real applications. Most notably, I think SKT in Korea started offering some quantum services along these lines. Of course, the long-term vision, which we do not know exactly how many years from now it's going to happen, is to have a global-scale quantum internet. And we do not yet know because we have two enablers that they're not fully developed yet. So this is to be able to distribute widely entanglement and also to have quantum memories, which means that we can store qubits, whether entangled or not. Now, of course, the most well-known application area and the most low-hanging fruit that people work on is the quantum key distribution. So just to offer you the motivation for that, essentially, nowadays, all encryption is based on these two principles. So there are mathematical, if you like, models that are computationally hard to break or to reverse. And they're modular. And essentially, they are heavily used every day by every citizen that access one way or the other the internet. And of course, RSA is one of the most important examples, and you see the complexity in time that it takes to break it, which becomes astronomically large if you use a key which is already 2,000 bits long. But of course, it has been shown that if you have a large enough quantum computer that does not exist yet today, you can break this kind of encryption only in 8 hours. So this is one of the main milestones that kicked off a lot of the activity, at least in the communication side. Now, the potential solutions to that, there are two. So the first one is more or less stay with the computationally difficult problems, but make it even more difficult. So it will be hard even for quantum computers. And that's a good approach. That's essentially what the national security agencies and standardization agencies are pushing out today, because it has minimal requirements in terms of changing your infrastructure. Of course, the downside is that still you have to assume that there are no new algorithms or new computing paradigms that can speed up or reverse these mathematical problems that you're trying to use. Now, the second approach, and this is the approach that I will be focusing on, is the quantum key distribution. So essentially, we're trying to distribute or exchange keys using security which is guaranteed by the laws of physics. And for that, it's true that we need substantial new infrastructure, new technology to be implemented network-wide, not only end-to-end. But if we do this, at least we'll be able to solve the problem once and for all. And by the problem, just to be specific, I mean the problem of exchanging keys, right? Not all problems of cybersecurity or all problems of cryptography. Now, a very exciting part of this story is that quantum key distribution is very interdisciplinary. So this is not something that we as communications engineers, we can solve ourselves, right? We have to take into account the entire network part, the device design, and we have to be able to talk with our fellow cryptographers and quantum physicists to be able to come up with a working system. In that direction, I would like to bring the discussion back to a couple of research topics that we have been working on. Namely, I will touch on two: network planning, orchestration, and last mile. So let's dive into the first one. So when we're trying to build the QKD network, one of the first problems that we have to solve is the network planning. Why? Because we still want to reuse the existing nodes that we have in our classic networks, and we still want to reuse the existing fibers that we have. So qubits are essentially photons that are being exchanged through these optical fibers that we use every day now for our classical communications. However, there are some particular requirements, and these particular requirements essentially is the fact that we have some link attenuation constraints. Because we cannot amplify these photons, according to quantum physics, if you amplify, if you try to apply any kind of operation on a quantum state, you essentially destroy it, you collapse it. So we can only prepare something, and the photon can run as far as it can based on the medium that it traverses. In this case, it's the fiber optic. And then we have to measure it and retrieve, hopefully, the information. So best case scenario today is, I would say, a few hundreds of kilometers that we can run. And this is best case scenario. It means that we can just exchange a few photons or very, very small key rate if we go to hundreds of kilometers. Usually it's tens of kilometers. So that already brings us into a situation that even if we have some blue nodes, as you see here, so essentially the green part that you see is our traditional network. The blue nodes is some quantum nodes that we want to interconnect. Why? Because this is where we want to exchange and cache our keys. And the purple nodes are some nodes that we can use just for facilitation. In that case, it's going to be just trusted repeater nodes, where we have to regenerate essentially the information, and we have to exchange keys in smaller distances just to close the gap. So one of the first research problems that we looked at, this is to appear in GlobeCon next week, is how to design a topology to minimize the deployment cost of a QKD network. So in that direction, we want to look at the original topology. We want to come up with a minimal graph that minimizes the number of trusted repeated nodes. And that we have to do for two reasons. First, because in a repeater node, the information goes back to the classical domain. So it's, if you like, it's a source of weakness in the system. And also, if you want to include many repeaters, then trusted nodes, then also it's additional investment. So we run this experiment in different topologies. So Restena is, if you like, the academic network of Luxembourg, but also NSF and DFN. There are other very widely used topologies in networking. And we try to come up with this minimum Steiner tree that gives us the connectivity among all quantum nodes and using as few trusted nodes as possible. And you can see the results. So this is something that we implemented using the minimum Steiner tree algorithm and a cost function based on the distance and also costs in case you have direct links between quantum nodes, or a larger cost in case you have to introduce trusted nodes. So this is the first part, when you just want to decide where you want to put your infrastructure, because as we said, we need additional hardware, and what kind of optical fibers, which optical fibers you have to set aside for this interconnection. And I didn't mention this, but keep in mind that when we talk about fibers for QKD, means that they have to be dark fibers, because they are very much affected with neighboring traffic if it comes in an adjacent carrier. So usually they're either dark, so we only send qubits through them, or we have a data carrier with a sufficient distance so that there is no interference between them. Now, moving on, we have to look at the orchestration part. So the orchestration means that how we go from the point-to-point exchange of keys to distribution in the entire network. And by distribution, we don't mean only real time, right? So how do you exchange keys beyond the point-to-point paradigm? And this actually happens by exchanging first keys in separate segments, and then traditionally sending back some messages through the digital networks so that you can establish end-to-end keys. But also you have to keep in mind that this is something that is constantly running, right? So this is running in the background, and we never throw away keys. We have to keep caching them because the key rates that we can support nowadays are very low. So we have to keep the keys even if they have to be used later on. And of course, another key challenge is that works rather well when we have full control of our domain or a network. But looking into federation of entire countries, you have to imagine that there are networks that are being controlled by different entities. So how do you orchestrate the key exchange between such networks? This is also a challenge. In general, in the literature, you find the two very rational approach, right? You either have a distributed system where every node has to operate independently, or I would say the most acceptable nowadays, also from the standardization perspective, which is the centralized. So as with traditional networking, we have been going more towards software-defined networks, centralized intelligence, centralized traffic management. Here also in the QKD, this fits very well. So you would have a single node that tries to orchestrate the entire network. Now, how this would look like? So you would have one of your nodes, which is responsible to orchestrate everything. And of course, it needs to exchange control plane messages with all the other nodes in non-quantum channels, classical channels that we already have. And this is to achieve different functions. First of all, to be able to synchronize point to point, but also on a system basis. You need to send control plane messages when you want to exchange, for example, keys between two nodes that are adjacent or not adjacent. Also, you need SDN and NFV control plane messages because you want to have some end-to-end encryption, end-to-end routing. And at the end, you also use this conventional IP technology to actually encrypt your data with the exchanged keys and send them over. So in the centralized mode, you have one node that is running the entire show. But this means that we have to be very careful, as I said, because key exchange does not mean necessarily that the entire system is secure. So you need to do an end-to-end security audit, and you might have to use the quantum keys also for your control plane messages, because you could have attacks that target your control plane. And an important bit of information that also QKD does not address is the authentication. So we always assume that the other node that we communicate with is not a malicious node that is posing for a neighbor. And again, this authentication is something that could be addressed with other means like post-quantum cryptography. So that gives you also the idea of the problems that we solve with QKD and the problems that we still have to solve with other methods. Now, of course, in the context of our national quantum network, so University of Luxembourg is responsible for putting that together with certain points of presence across the country. So right now we have only a link running between our two campuses with 33 kilometers away. We have commercial grade equipment which can exchange key rates. These are very low, as I told you. This is key rates in the number of kilobps. But of course, we envisage already a much larger architecture, so QKD devices with some SDN, NFV infrastructure on top of them for the orchestration. And the next step for us would be essentially to try this network-wide orchestration and go beyond the point-to-point experiment. Now, another area which I would say it's very basic research, but it's also very interesting, is the last mile. And by last mile, we mean that we know that most of us access the internet through portable devices. And the portable devices don't have optical fibers coming there. And it's the last mile, it's most of the times wireless. And we recently published some work that is trying to address this last mile. So how you could essentially exchange securely, let's say physical air security enabled by QKD on a RIS environment. So RIS is also a very popular research area in 6G, and it's meant to enhance coverage by adjusting the electromagnetic environment. But here in the figure that we see, we envisage a RIS which is even more capable. So you have the classic electromagnetic spectrum, which is for data. But at the same time, you can use the RIS as a trusted node. So it means that you have free space optics. And as you can exchange qubits over fiber optics, you can also do this over free space optics. And you can have a trusted node in the middle, which is the RIS, and trying to establish secure keys all the way to your devices. And once you have these end-to-end keys, then you can start transmitting encrypted data. Of course, this is a bit futuristic in the sense that this assumes that you have both RF and some kind of FSO on your devices. But you know that there is a lot of interest in visible light communications, for example, or other forms of free space optics. So you might be able to see some paradigm like that in the future. In any case, this was a recently published paper that you might be interested to have a look at. Here I just have some results that I'm not going to detail, but in general, what we do is that we measure the bit error rate of the end-to-end communication and trying to show that the bit error rate for the intended users is not higher than it's not lower, sorry, than the eavesdropper. And that, of course, depends on the number of RIS elements and on the locations. But yet again, this is not something that you can completely reproduce as you do it in the optical fiber in terms of unconditional security. Okay, then I'll move on to the quantum internet. And again, starting from more tutorial level introduction. So as I said, the long-term vision is to have quantum computing networks, as you see it here. This is the top of the pyramid. Today, we are at the bottom of this pyramid. We are in the trusted repeater networks. And to go higher, we essentially have to develop some efficiently some technologies that we don't have at this point. So prepare and measure, we do have. So we can prepare and measure. We can do entanglement generation up to a point. In the lab, it has been shown. Even over satellite, it has been shown, but it's not really commercially available. And even more importantly, the quantum memory is not something that we can very easily reproduce. So the largest time frame that we can store qubits, this is kind of scientific experiments in the state of the art, is about 6 hours. So you see that we are very far away of having quantum memory, which is reliable, and we can use it to go into the upper layers. Of course, above that, we need to have a few qubits which are fault tolerant, and then we can go to the quantum computing and enable all the applications that you see here. Now, in QKD, this normally does not appear, so we do have entanglement-based QKD as well, but in quantum internet, it is well accepted that the main network resource that we need to generate and distribute is entanglement. So if we have entanglement between different nodes, we can do many other things, even without communicating qubits. And I will show you in a while some examples of that. Now, to do the entanglement, what are the bottlenecks today? First of all, the bottlenecks is that we can do an entanglement between 2 points, but of course we still have this, if you like, attenuation constraints. So usually if we want to exchange entanglement from nodes that are not directly connected, we have to do some protocols and exchange point-to-point until we reach an end-to-end entanglement. And this, of course, is something that comes with an overhead, because every operation, it actually consumes entanglement. So the furthest away you want to have entangled qubits, the more you have to consume to achieve that. On top of that, entanglement is not something that you generate once and it stays forever, right? It's something that quickly degrades. As it interacts with the environment, it degrades. So in a way, just to maintain over time some pure entanglement or distilled entanglement, you have to consume imperfect entanglement just to maintain that. So you see, the process is more easily said than done, because there is a continuous, there should be a continuous way of distributing, generating this imperfect entanglement and running a constant processes behind them just to keep this precious network resource alive. But why do we want this? I mean, why do we want this precious resource? And we'll give you some examples here. First of all is the quantum super dense coding that you might have seen. So if Alice and Bob, they share an entangled pair, and now Alice sends a qubit to Bob, if you combine the two, you can transmit 2 bits of information. This is with a couple of sentences, this is how it works. And that could help us how? For example, we could be sharing entanglement at off-peak hours, and then we can do super dense coding at peak hours, and then we can increase the level of communication when we have essentially peaks in our traffic profile. On top of that, since we have only a single qubit in the channel at any given time, this is inherently secure. So it solves also our quantum security aspects that QKD was addressing in the past. Now, on top of that, with entanglement, you can do quantum teleportation. So Alice and Bob, again, they have a shared, they have an entangled pair of qubits. And after receiving only 2 classical bits, so there's no quantum channel, you just send 2 classical bits, and Bob can exactly reproduce a qubit state that was on the Alice side. Again, if you see it like that, it's difficult to appreciate the value, but if you see the implications, it's very important. So essentially, it means that we can be having quantum states that move around in our network without the need of a direct physical quantum link. And this is why we expect that the quantum network will be very much, say, very sparser than the classical digital network. But with the help of these techniques, you will be able to exchange quantum states from one point to the next, even if there's no quantum link to connect them. And of course, it also, the same method is the one that entanglement swapping is based on. Now, of course, in the future, and this is something which we're still far away from, we want to have a physical graph where we can exchange entanglement as a resource between any node of the system. And that means that we will have to have different steps to enable the end-to-end connectivity, as I mentioned before. And this is a very active research area. So from mainly the experimentation part, because analytically we can take this as given, but really to make something like that possible in the lab and even more difficult in the real networks, this is a process of ongoing research. And here you can see how by doing different steps in your network, you can establish an augmented link which has entanglement end-to-end. And of course, there are even more complicated versions like multipartite entanglement, but I will not go there. Then I think because we're very much used to the conventional stack of our IP networks, it's good to think how the quantum network stack differs from what we already have. And there are similarities and there are differences. So similarities is that we still want to have some separation of concern, right? So we still want to have layers. And we can still get some primitives from the classical network. So we can still the same or similar addressing node, control plane signaling, network synchronization. However, the nature of the layers and what they exactly do will be very different, especially when we go into entanglement. There are several proposals that have been published in the literature that we can quickly go through. So these are some of the proposals that you see in the literature, how you build a quantum internet stack. And you see that more or less they try to follow a similar layering structure, like let's focus on the middle one. So physical layer, link layer, network, transport, and application. But you see that the target or the functionality is very different. So the physical, it's mainly to attempt to create entanglement because it's not a perfect process and it doesn't always work. There is a probability of success. Then the link is to make sure that you have achieved entanglement and you have a robust entanglement. Network is to do the swapping and make sure that you essentially have end-to-end entanglement. And then transport is to do the qubit transmission, and then you have some application running on top of that. You see there are other flavors as well, which depends on exactly what kind of entanglement you try to achieve, whether it's point-to-point or it's multipartite. But you get the gist. And of course, as the group works very closely with NTN, we have already started thinking at the applications that are related to quantum and satellite networks specifically. And the first part is quite well understood, and it's something which we already have demos, mainly from Chinese colleagues, and also now there is a plan to have a quantum QKD network over satellite in Europe. And the motivation is obvious, and I think this paradigm is well understood. And the premise is the following: because the attenuation is smaller through free space optics, if you want to go further from point to point, it might be easier to go over a satellite rather through a very long optical fiber on the ground. So this is as simple as you can put it. And then in this case, obviously, satellite somehow acts as a trusted node. But we want to see even beyond that. We want to be more futuristic, and we want to think about why would we do a quantum space internet. And there are some, I would say, reasonable ideas or arguments. First of all, if you have free space optics that do not have to cross the atmosphere, you suffer less from decoherence. So inter-satellite free space optics are important. This is very energy efficient because essentially you modulate your bits on single photons. It doesn't get more energy efficient than that. This is a particle that carries your information. And you might have, again, this is not always the case, but you might have more efficient cryogenics in space. And cryogenics are very often used for quantum physical air devices. Of course, you have zero carbon power generation and so on. So there are some arguments that we might be going there, but of course, this is more of a long-term vision. Now, just to cover a couple of topics, and I'll try to speed up just to make sure I cover everything. So we have two main topics. One is signal processing aspects, and the other one is more network load balancing in this direction. So in terms of signal processing, we want to very often estimate, as we do channel estimation for classical systems, we want to estimate time-varying quantum channels. And of course, if you have IID conditions, this is straightforward. But if the channels change, you have to operate with a trade-off. So you either do continuous channel estimation, or you simultaneously communicate and try to estimate your channel rate. And it's not clear how many samples you should be using and what coding rate. So we recently published a TCOM paper that tries to look into this problem. So here you see the parameters of a poly channel. This is one of the most well-known quantum channels. The solid line is the actual thing, and dust line is the estimation. And you see that we don't really estimate very well with a high coding rate due to the communication errors. Now, if we do adaptive coding rate, this improves, but we end up having a delay. And if we combine adaptive coding rate with adaptive number of samples, then we see that we can achieve a very nice and accurate estimate. And of course, there is a nice channel emulator that we built to run all these experiments. You see here the GUI. Now, the other side of the coin, and this is always trying to bring some signal processing perspectives into the quantum physical layer, has to do with the variational estimation of optimal signal states. So assuming that you all know about the basics of information theory, you know that for every channel we can optimize the input distribution. So this is more or less trying to do that for a certain class of quantum channels. And we try a very general scenario where we don't have a description of the noise, right? So we don't know that the noise has a specific structure. What we're trying to do is we want to find the optimal signal states that they maximize the trace distance at the receiver end. Why? Because that means that we can very easily discriminate one state from the other. Again, we're talking about binary states here. And we tried this into two very well-known channels, the amplitude damping and the polychannels. Now, the approach that was followed, I won't go to all the details, but just to explain to you the graph. So we prepare some states, we transfer them through the channel, and then at the other end, we can estimate, to be exact, the distance trace. This is fed back, and then we have a classical computer who's trying to optimize a parameter that is dependent on this trace distance, and then feeds it back. And then this is like, if you like, an iterative process that is trying to optimize what kind of input quantum states we give to this channel to have the best performance out of it. Here you see some nice examples of how we converge to the optimal point. So the optimal point is the black. You see more or less ground truth, which is the green, and what happens with a number of iterations that we run this optimization. You see that more or less we always converge to the desired point. Same here, just for the sake of time, I will skip through it. And then we go to the second part. So at least I have 15 minutes to cover that. I'll again try to be quick. So this is quantum optimization for quantum problems. And why this is important. Everybody's talking about 6G and how we want to have KPIs that are growing larger and larger. But of course, these scaling factors are not easy to handle. We have scaling factors in number of devices, interfaces, antennas, bands, standards, access points, service types. And of course, we want to have orchestration. It means that we want to optimize all that jointly. So you can imagine that the combinatorial problems that end up from this kind of system models are very, very large and very, very difficult. So what quantum computing promises to do, it hasn't done yet, but promises, is to come up with scalable solutions that address these kind of problems. And of course, the status of quantum computers is that there are a lot of, I would say, articles that claim quantum supremacy, that quantum computers are better than classical and so on. But if you really look into the details, we can only show this for particular applications that are not so practically relevant. So for the problems that we want to solve, we cannot really demonstrate some quantum supremacy or advantage as of now. But we hope it will come into the future, and that's why we're investing in this kind of solutions. Now, so when to expect this practical advantage? Again, this is kind of everybody's guesstimating. So right now we are in this NISQ area, so the noisy intermediate scale quantum computing. And this is called like that because essentially our current qubits are so noisy that we are not always below the error correction threshold. And what is the error correction threshold? There's a line that essentially, if you are below it, you can apply forward error correction, and you can include some overhead in terms of additional qubits, just to make sure that you correct errors that happen. But if your qubits are above this threshold, they are so unreliable that even if you introduce FAC, then actually you create more errors instead of solving more errors. So we're still waiting to get into this area where you have some kind of fault tolerance, but we're not yet there at this point, right? And we're not very sure when this will happen. However, with what we have to do, we can still solve some quantum ML with small data and large processing. or algorithms that have small qubit requirements and frequent measurements. So small scale problems at this stage. And of course, we expect or we hope that with time, we'll be able to demonstrate these concepts of quantum utility, which means that we can solve a problem with less computing time, less power, or more accurate results, and eventually go to quantum dominance. So this is all the, if you like, the hopeful messages that push researchers to work in this area. Now, two aspects I want to touch in terms of actual and tangible applications is the variational quantum computing and QAOA. So essentially, there are some combinatorial problems, and here we're tackling the binary knapsack problem that you might have seen. It's very well known. And this is one of the problems that we can reformulate and tackle it with a quantum computer. And in 6G or in any communication network, there is a lot of scheduling, resource allocation, access control, a lot of problems that can be modeled under this knapsack framework. How we tackle it usually is that we start with a problem description. This is the classical optimization problem. We have to find an equivalent Ising formulation. This is when we kind of cast it into quantum states. Then we input it into a quantum circuit that runs some steps. And then we measure and iteratively work with a classical optimizer. So this is the hybrid model where you have a quantum circuit working in tandem with the classical optimizer. So this is how we did the modeling. So I won't go into the details, but this is the quantum circuit that you can apply. This P equal to 1, 4 items of input, just one stage. And here you see some of the results that we get. Maybe I go to the next one. So more or less here you see number of measurements that you need to reach an optimal state with good probability versus the number of layers. This is the depth of your quantum circuit. So if you like, one is the iteration that you use through your classical system, and the other one is the depth of your quantum circuit. Similarly, there is another, if you like, flavor of quantum algorithm, which is called quantum annealing, and we try to apply it as well in an NTN communication system for beam placement. And this we actually modeled as an NP-hard click cover problem. And in the quantum annealing, we have to do some reformulation to make sure that we bring it again in the right form. But in principle, this works quite differently than the other one. So the basic principle of quantum annealing is that you want to go from high energy to low energy, and this is how a quantum system naturally evolves. So you can start from a superposition state, and eventually you can end up with some bias that is dimension to the solution that you want to achieve. So the entire premise is based that if you start with high energy system, then eventually you'll go to the ground state, and then you can use the eigenspectrum just to reflect your solution, right? So this is some evolution of the quantum system, natural evolution of the quantum system that can lead or can be aligned to your optimization process. Similar here, we have some examples. Here we focus more on the D-wave, if you like, computing paradigm. It's one of them. Some people use IBM, Qiskit, and so on. So essentially, we do have access to quantum computers now in the cloud, even though for very little time and very expensive if you want to go beyond that. But these are experiments that we actually use quantum computers to test them. And here you can see some of the results that show that we can successfully find feasible solutions. And depending on the parameters, you can see that we really get nice solutions close to the lower bound. Now, just to conclude, I wanted to give you a bit of an intuition of what we can look for as the research evolves in this area, and what is interesting, at least from our perspective. So again, I split it in two parts. One is the research roadmap in comms, and the other one is computing. So in comms here, you can imagine that we are at the same stage as in the very early stages of the digital communications. So there is still a lot of open problems in terms of information theory, quantum information theory, performance evaluation, finding out capacities of simple quantum channels. Even beyond that, we want to look into more applied channels like inter-satellite quantum channels that might be applicable to the quantum space internet. Satellite quantum networks, because this is going to be the first, if you like, implementation of QKD. And then also look at the quantum network utility, which is, if you like, a metric to evaluate what we can do with our quantum networks by capturing a large scale of or large range of applications. But on the other hand, and I think that's also very interesting for our community, there is also the achievability, right? So it's not only about what we could do with many various ideal assumptions, but how do we build systems today? And in this direction, the quantum error correcting codes obviously are very important, and at the same time, the channel estimation or input state optimization along the lines of the work that I presented before, they are also very fruitful research areas. Now, looking at quantum computing, this is also, I would say, very interesting. The algorithm design, the complexity analysis is the most important. Obviously, trying to find even some applications that we might be able to show some quantum advantage in relevant areas. So that will definitely give an extra push to this scientific community. Noise estimation and benchmarking protocols, they're also important. Quantum error corrected codes are relevant also here, because when we talk about FEC as communication engineers, we always think about essentially repairing errors in our channel. But here you have to imagine that the coherence actually happens as we speak in every quantum computer. So there has to be a constant error correcting capability just to make the quantum computer run. And of course, talking about 6G MEC, mobile edge computing, whether it makes sense to have some kind of quantum computers in some part of our architecture, how we connect them to classical computers. This is some, I would say, low TRL ideas that you can find out there in the literature, and they're worth further investigation. So with that, I will conclude, hopefully in time and with 5 minutes to spare. Here you can see some relevant references and some projects. So the slides will be made publicly available, so you can download them, you can click on the links or look for any further information. And with that, I will conclude. Thank you very much for your attention.
Thank you very much, Symeon, for this very nice presentation and very informative one. Let me open the floor for questions. Yes, please.
Excuse me, can I ask a question?
Yes, of course.
Thank you. First of all, thank you so much for your very interesting presentation. Actually, I just want to know if quantum machine for large processing data, does it actually work for IoT communications? Because my research path is vehicular communication and Internet of Things communications, and I'm working on application layer and network layer. And it seems that quantum communication is more secure than any communication that I researched. And I'm just asking question if we can combine the artificial intelligence with quantum communications, and also using federated learning or federated cloud for quantum memory optimization? Because right now I know federated cloud can help with like large real-time processing data, and it can be efficient with using like edge computing, fog computing, and cloud computing. But I don't know if it can be integrated with quantum computing or not.
Yeah. So many questions in one, so I'll try to answer one by one. First of all, you mentioned vesicular and IoT networks and so on, and quantum comms on that. So as I said, right now, quantum comms, at least practically speaking, is mostly relevant for fiber optic networks. So we hope to see more and more FSO, but FSO for moving terminals, this is an even more difficult challenge or proposition, right? So it's not the first target, I would say, to use quantum comms for moving terminals. The second question had to do, I think, with quantum machine learning at some point. And the quantum machine learning, it's something that has shown some premise, but essentially you have to keep in mind that there is a large overhead if you want to convert very large data samples or data sets into the quantum domain. So in principle, quantum machine learning works very well if your data set is already composed of quantum states, because then you skip all this overhead, and then you might have some benefit. But if you want to do all this overhead of having digital data and then kind of reflect them into quantum states just to solve with quantum means, it doesn't always mean that it's a more efficient solution.
Oh, thank you so much. Thank you so much.
And then maybe, I think you mentioned federated learning also, that just to cover that part, I think, yeah, it's not more federated learning, but distributed quantum computing, which kind of goes in that direction, is something which is very interesting today. Why? Because we don't have large computers, we only have small computers, and it's very interesting how to make these small computers federated to solve problems in parallel, right? And this means that for that, you would need to exchange directly quantum states between distributed quantum computers. This is also one of the premises of quantum space internet. So this is really a very interesting area.
Yeah, so if I understand it, if I get it well, you mean federated learning might be effective because of the distributed nature of the learning?
Yes. But I mean, again, federated learning has a particular notion of exchanging smaller parameters, smaller models to achieve some kind of privacy.
Exactly.
So that part, it might be the way you do it, or you might also just start from general
I
quantum computing problems.
Okay, because I recently graduated with intelligent network traffic prediction in vehicular communications. And as a future direction of my research path, I noticed that quantum computing could also be helpful for 6G and beyond communication between vehicular network, and also is more secure because of using quantum computation. But I'm right now I'm working on using an efficient artificial intelligence for vehicular communication, and federated learning seems to be more secure because of preserving the privacy of data, and also because of the memory that needed. It can be used in edge. So we have federated learning in edge for vehicular communication, and that's why I just want to know if it might be useful to use quantum communication to replace these edge AI for vehicular communications.
Well, it cannot do both. I think you either use the
Okay.
quantum computing just to speed up some problem because you have better complexity scaling with the dimensions of the problem, or you use quantum communication for better security, but it doesn't solve both problems at the same time, right? Kind of different paradigms.
Thank you so much. Yes, thank you so much. It's really, really helpful for me. Thank you so much.
Thanks for the question.
I really appreciate your
question.
Thank you.
I see Fabiana Pivet has raised her hand, so please, Fabiana. I don't know if I'm pronouncing correctly.
I can go if Fabiana is not ready.
Yes, Ali, please.
Thank you, Professor, for the remarkable presentation. Pretty interesting. I have a curiosity question about how we maintain entanglement. I know how difficult that is. I just want to know about the technologies used today and what's going to be used in the future. Thank you again.
Yeah, so as I mentioned, this is like in practice, this is going to be a continuous process where you essentially generate imperfect entanglement. You distribute entanglement and you make it even more imperfect. And then you end up having some imperfect pairs in two places. And to create perfect entanglement, you just consume and you combine these imperfect pairs to improve their quality, right? So depending on this overhead and those probabilities, usually in scientific problems, they model this as probabilities of success. Then you have compound probabilities that define how successful is your network. And of course, you see, because there are many processes and every process is adding its own uncertainty, at the end, you might have a very large overhead, which means that just to achieve one perfectly entangled qubit, you might have to, I don't know, generate hundreds of them and communicate, I don't know, 50 of them just to, at the end, reach with one perfect entangled pair. So, and this is, I would say, one of the most difficult challenges going to the next stage of quantum networks, how to have this entanglement as a network resource, and how, of course, do all the orchestration, resource management, scheduling behind it, because all that has to be well timed, right? Because time works against you in the coherence aspects.
Food for thought. Thanks a lot.
So let me go again back to
Hello?
Fabiana.
Hello?
Hello.
Do you hear me?
Yes, we can hear you now.
You hear me, are you sure?
Yes.
Okay, great. Yes, I wanted to ask you actually if in Luxembourg you have some activities related to the combination of QKD and post-quantum cryptography, and if there is any manner in which a hybrid implementation of QKD and post-quantum cryptography could eventually change the quantum network planning and the orchestration. Well, I think orchestration, yes, but the quantum network planning, would there be any effect from a hybrid QKD PQC implementation?
Yeah, that's a good question. So essentially, we combine it, but for different functions. So
Yeah, I know. I was asking if there is somehow an effect from the upper layer to the lower, really to the physical layer. I don't know if you see it.
So we ideally we would use post-quantum in the future for everything else apart from the key exchange. So some things like the data encryption end-to-end, it's still quite complicated as it is today. It's not in danger, but once you have post-quantum algorithms that can give you much better security and they're well implemented, then I don't see any reason why you wouldn't use them for everything that does not need to exchange keys. So QKD will be mainly for the key exchange, and then for your authentication, for your encryption. For digital signature, you might have all of them implemented with PQC. And it's a nice combination of technology, but we have also to think about the innovation and potential. Because it's true that PQC is the low-hanging fruit, but in terms of innovation, it's still different software, more complicated software that we'll have running in our devices, maybe some hardware implementations that are embedded, but it won't create a brand new digital ecosystem or a new series of startups that do something completely different. And QKD really is bringing up this completely new paradigm that I hope that QKD is only the start of it, and then eventually these startups and this innovation ecosystem will go ahead to build the quantum internet as they build better and better technology. So in terms of European innovation, also because maybe that interests you, I think that this is why it makes sense to look at QKD now, not only just for the cryptography, but more for the future of our networks.
Yeah, sure. I fully agree. I mean, well, not fully actually. I agree to a large extent, but I also do believe that the PQC will also be able to create somehow a new ecosystem. Although, okay, it will be a software one, but by reinventing maybe the way we authenticate for some applications, maybe we will also somehow invent new ways of using applications. So the paradigm shift will not only be in terms of QKD devices, but maybe also at the levels of applications and transport layers. Well, we will see.
Yeah, it's correct what you say. I mean, I agree that PQC you have to change the upper layers, application, maybe transport, but really for QKD, or if you want to think about quantum internet in the future, you have to reinvent everything from scratch.
Yeah.
So that's why the innovation potential is much larger. Now, how many years in the future this will happen, I cannot predict right now, but that's why I think it's worth devoting some effort in this direction.
Yeah. But would you have any test that I don't know if it has been done in Luxembourg about a mixed implementation QKD PQC?
Not at this point. Now we are at the point we will use the exchange quantum keys, but for traditional AAS, if you like, encryption. Okay. So to set up some VPNs. But we have expertise in the center. We have a cryptographic group, which is part also of our national QCI project. And they will be looking into post-quantum solutions. And then I'm under the impression, because this is also a bit beyond my area of expertise, that there are open source implementations of the most, if you like, potential candidates of PQC.
Yeah.
And then we could potentially integrate them because our upper layers of architecture are completely software. So we can very easily replace one algorithm with the other if we want to test some demos.
Mm-hmm. Yeah. Okay, great. Thank you.
Thanks, Piano.
Thank you very much. I don't know if there is any other. Oh, I see there are several more questions. So, Konstantinos, please. Konstantinos, we cannot hear you.
How about now?
Now it's much better.
Okay. Thanks again. Thanks, Symeon, for the excellent presentation. Very, very informative, as always. So a quick comment for the, we are coming from Luxembourg, so the question is going to be about the space segment, space part of the QKD network, the exchange of keys. And how do you see the issues of using LEO satellites in general for the exchange, the time required to move from one place to the other, and the duration that can spend over a particular area? I mean, is there going to be a bottleneck? Have you looked into that at all? And at the end, what would be the solution in this case? So multiple beams plus multiple satellites, or
that's a very good question. So essentially, there are a lot of active researchers, actually papers that were published a few months ago that are looking into this subject. Of course, we know that our first attempts will be with a single satellite in Europe, which is being built. But if we want something operational, obviously we need to have a constellation. And we have a constellation, and it has to be quite dense if we want to increase our key rates. And at the same time, a lot of these studies, they take some impairments into account, but they forget some of the impairments that are always very problematic. For example, if you have some rain attenuation, some fog, and so on, this is really a deal breaker for free space optics. And the orientation doesn't matter. Usually, if you have a cloud on top of you, when we're talking about satellite communications, it's really on top of you. From whatever direction you see it from the sky, the cloud is really on top of you. And that's a very difficult problem. Of course, there are fancy FSO methods looking into diversity, looking into MIMO that are trying to kind of address this. But I don't think these are high TRL enough really to be implemented today. So today we still want to have a very clear sky, hopefully during the night, to be able to reliably exchange keys. And this is the bottleneck that means that we need a very dense constellation.
That's very true, actually. And maybe the fact that we need to look into the memory, quantum memories on board, maybe that would be another major issue. I mean, for Cyprus, you know that we're an island isolated, so there was no other option for us. But the good thing is that we have mostly good skies, clear skies. But we need to connect to some place in the mainland Europe. So, so yeah, somewhere has to be nice sky around Europe, somewhere.
I cannot promise that for Luxembourg. I can tell you that.
Yeah, no, definitely not. Thanks a lot.
So let us go to Ioannis. Ioannis Coaches.
Yes, can you hear me?
Yes, we can hear you.
I would like to ask, in your network in Luxembourg, which vendors' QKD systems do you use? And if you use the same dark fiber for both the classical and quantum channel?
So at the moment, we only have equipment from IDQ for our one operational link that we have today. And we are using, or we have tested it only on a clean dark fiber. Now we're in the process of running the multiplexing experiment. So we have different pairs from IDQ. One of the pairs that we have supports multiplexing in the same line. And this is something that hopefully will be done in the next few weeks or months just to test. Of course, this is something I would say very desirable because I've been very much involved in procuring dark fibers, and this is not cheap. So if you can pack essentially multiple channels in one fiber, it could be quantum digital, it could be quantum also. This is another experiment that you could try. So that is something that would help very much to motivate the implementation and to lower the cost. But we haven't achieved that yet at this point.
Yes, that would be very cost efficient to deploy. And a third question, because I saw in your presentation the variational algorithm, if I remember well, and there is a classical computer in the middle of that chain process of those quantum systems. Was there an attempt to use a quantum computer in order to implement that part that the classical computer does?
Yeah, so unfortunately, this is the case in most of the quantum optimization or quantum computing paradigms as well. Because most of the problems that we have, and in terms of input and output, it's in the digital domain. So even in any kind of IBM cloud computers that you have, always the input is somehow provided in the digital domain and the output in the digital domain. So there is some transformation process in between. In the particular algorithm, this is the structure of the algorithm because you know that the quantum circuit has been aligned with the Ising formulation to the problem that you want to solve. But again, if you want to run iterations, it's much more efficient to do it on the digital domain. because in any case, you want to, at some point, create quantum states, you give us input, and you want to measure the output. And then this is the place where you can have a separate search space, which is the classic digital world. And very often, to do these iterations, there is no added value of doing it with a quantum computer. I mean, this is not one of the problems that quantum computer can speed up. So it would be an overkill to do this with a quantum computer.
Thank you.
So there is a question in the chat, but I believe that it's quite difficult to answer right now. I will read it, of course. It's if I want to establish a quantum communication lab at my university for the quantum research, can you please list down the equipment I should have initially?
Yeah, so maybe I won't give, I mean, I cannot propose vendors because this is, I would say, personal choice. But what I can say is that if your focus is on quantum communications, there is a main limitation today, main bottleneck. So the fact is that quantum devices are very difficult to manufacture, and everyone is manufacturing, every vendor has their own, I would say, very sensitive device. And when you acquire it, more or less you have to use it as is. There are very little things that you can tweak because there is a danger that the system no longer works. These are very sensitive systems. And the problem that we have right now is that this more or less means that our physical layer, once you buy these quantum devices, is fixed, right? So you cannot really touch the physical layer, which goes against everything that we believe, because in classical digital communications, we know that there are so very flexible software-defined radios, for example, that we can more or less touch everything we like, and we can deploy our nice algorithms from one day to the next. So if a startup company could do something like that in the quantum domain, I think that would be a very big deal, and that would very much accelerate the adoption of these systems by academia specifically. Because right now, yes, we buy them and deploy them, but we cannot really touch them. It's a black box to us. And that's not really what we like as academics. Like, we want to be able to tweak everything that we can in the labs and in the equipment that we acquire.
So let me also go back to Fabiana. She has one more question. So please, Fabiana, and sorry for not seeing you earlier.
Hi, do you hear me?
Yes, we can hear you.
Okay. So I want to ask to Symeon somehow a strange question. If you would have the possibility to launch something in space tomorrow in a low Earth orbit, something of benefit for quantum communications or for the future quantum internet. Let's be ambitious. I mean, let's think really about something for the future beyond the prepare and measure networks. Would you have an idea what would you like to launch?
Yeah, so I think what would be very interesting to try to reproduce would be the entanglement-based methods for space, which unfortunately we're not front runners in this. There are other continents that are doing much better than us. And I think in this case, we should really speed it up and being able to catch up and reproduce some of the methods that have been already proven worldwide. However, the problem is that we know even now with EDU-1 and so on, which is the European quantum satellite which is being prepared, is that these are quite new technologies, and even the industry is learning how to use them today. And it means that they cannot really be implemented in the small-scale CubeSat that we normally use for experimentation. So all in all, if we had this kind of blank slate check to do some ambitious experiment, it will still have to be a much larger satellite than a CubeSat just to be able to achieve these technologies. And this means that could be a quite expensive endeavor. So I hope there will be some future calls for this direction. But we also have to keep in mind that maybe a message for the funding instruments as well, that we cannot really skip steps. So being very specific and talking about the competition, which is our colleagues over in China, they're doing very well, right? So I think they followed the steps of doing the research and then going into higher TRL, where, until they manage to have something working. And now in Europe, we're in such a hurry that we are essentially pushing a lot of very difficult targets to the industry. And I hope we manage. But it always makes sense really to have some prototypes, some early stage research in the lab before we throw these difficult problems directly on the industry's shoulders.
Yeah. Okay. Thank you. Thank you very much.
So let us go then to Saad. I don't know if I pronounce correctly. Saad or Sayad. Ahmadpur, I believe. Can you hear us? I see that he has a question in the chat, so let me read it from there.
Can I ask a question?
Yes, of course, please.
Can you hear me?
Yes.
Okay, I have a important question regarding quantum computing. I am working in the quantum computing and designing the some of the important quantum computing is actually circuit based on a quantum computing, and I have an important question: how we can connect my circuit that I implement all of them based on IBM reversible logic quantum dot with one software. Is there any specific, let's say, software that we can connect and run all of my circuit hardware or not?
So I'm just trying to figure out the question. So if you're talking about running some gate-based quantum algorithm.
Yes, gate-based. Exactly. Yes, exactly.
Gate-based, right?
Yes, exactly.
So there are different softwares for that, different platforms. Some famous one is the IBM Qiskit. And then obviously you have to decide whether you want to run this on a quantum computing emulator, which means that you emulate quantum computing functions on a digital computer, or you want to actually run it on a quantum computer, which is in the cloud, because you cannot buy a large enough quantum computer right now.
Yes.
So both options are available. So if you go, for example, to the IBM framework, they have both emulators, and you can actually use them for a few minutes. They're quantum computers that are in the cloud, and you can do either or. And the last thing that I haven't done myself, but I heard that from some colleagues, that you can buy, if you like, off the shelf, very small few qubits quantum computers for a reasonable price, right? I mean, these are toy examples. You cannot do much with it because you just have a few noisy qubits.
Yes.
This is another way that you could go.
Thank you so much for your response. I wrote one project for. Right now. I am working in the quantum computing in Turkey, and one of the concern that some reviewer said to me, yes, it's very great that designed a lot of circuit based on a quantum computing based on, let's say, IBM reversible logic and these kind of things. But the problem is how we can implement in the real world. If we compare. If we see the budget and if we want invest money, it means we should pay maybe more than the $10 million, and I don't know, maybe more than.
Yeah, and, I mean, I wouldn't promise to build it myself, but what you could promise, assuming that it fits on your project budget, is to lease some quantum computing capacity from one of the cloud providers, and that would be hopefully an eligible expense. And then you say, I don't implement it myself, I don't have a quantum computer, but there's a framework, and I can show you that this algorithm was really run on an actual quantum computer. And that might be sufficient, that's a suggestion.
Thank you so much. Thank you so much, Professor. I really appreciate it.
So there is one last question, and I see that a student of ours in the university sent me the question personally. So let me read it to you, Symeon. It is clear that progress in material science influences the progress in quantum computing. However, is it possible for already developed techniques used in digital and analog communication to be used, or there is a need for innovation on the sector as well?
Yeah, so depends on which layer we are talking about. For example, all these devices that you buy from the vendors, and we treat them as black box. Essentially, they have some digital IP which is encoded into their FPGAs, right? Obviously, we don't have access to that. It's by no means something that they would share. But a lot of these protocols and forward error correction codes, which are still digital, not quantum, they're being implemented in their FPGAs. So up to that level, when we reach that level, I think we have all the knowledge in the community to already start contributing with actual and very, I would say, high TRL input. Now, when you go below that layer, when we start talking about the physical layer and the quantum dots, for example, quantum dots is some devices where they're trying to generate single photons. There are many other methods. So that we really go to the intersection with the physics department. This is what the physics departments actually do. So I think we have to really be in touch with them and try to interact for the interfacing between what they know how to do very well and what we know how to do very well. Right? Because there's no single community that can on its own design such a device. It's really an interdisciplinary exercise that has to be run.
Once again, thank you very much. It was a very informative and interesting talk.